We have been talking about the induction machine for quite a few videos. An important tool for us to understand the induction machine better is to use the equivalent circuit. But before we talk about the equivalent circuit of the induction machine, let's spend some time to discuss the basics of electric circuits in general. The two most fundamental concepts are the current and the voltage. We've been using these two concepts in our previous videos without explicitly describing them. The concept of electric current is actually very similar to that of water current. Suppose we have a water channel with some collection of water inside of it. Right? If the two ends of the water channel are at the same elevation, and the water is at standstill at the beginning, then the water will not flow, and the water current is zero. Now suppose we raise up one end of the water channel so that the two ends are at different elevation. Then the water inside the channel will flow from higher elevation to lower elevation. And now we have a water current. We can quantify water current by sort of measuring the amount of water passing through, say, a unit cross-sectional area of the channel within a unit amount of time, right? And we call that the water current, right? Which is basically the rate of change of the amount of water at a particular location, right? That's what we call a water current. And we can think of an electric circuit just like a water channel, except that the stuff that's flowing inside of it is not water molecules, but positive electric charges. So the voltage is just like elevation. So positive electric charges will move from higher voltage to lower voltage. It's just like water flowing from higher elevation to lower elevation. So if there's a voltage source, such as a battery, right, inside the circuit, then the positive terminal, they call it a terminal, the positive terminal of the battery, which is usually represented as a longer bar here, right, it's going to have a higher voltage than the negative terminal, which is represented as this shorter and thicker bar here, right. So positive charge will flow. So positive charges will flow from the higher voltage terminal to the lower voltage terminal. And in this particular cycle, in this kind of a process, in this kind of flowing process, it's going to drive different kind of electric components, right? In this particular example, it's a resistor and an emitter and a voltmeter. Those are components, right? So if we measure the amount of positive charges passing through a certain point, say this point, right, on the circuit within a unit amount of time, what we can obtain is the electric current. Basically, electric current is just how many positive charges are passing through a certain point within a unit amount of time. It's basically the rate of change of positive charges at a particular point, right? And this measurement can be done using an instrument called an ammeter. This kind of thing, which is usually connected in serial within the circuit. The ammeter can be treated just like a copper wire with almost no resistance, so it's not disturbing the circuit in any way. So, which is a good thing, right? If you are trying to measure the current, but if the measurement the measurement instrument itself, if it's going to disturb the circuit, then it's not a good thing, right? You are not getting the accurate measurement. So ammeter has almost close to zero resistance, so it's not going to change how the current actually flows through it. So if there's no resistance through a certain segment of the circuit, so no resistance from this terminal pass through the ammeter before it reaches the resistor, right? Through the entire segment, there's no resistance to it, right? If that's the case, then the voltage will not change throughout this segment, right? So from this terminal to this terminal, there's no changes. There's no changes. There's no resistance. The emitter has almost zero resistance, right? No resistance. So the voltage here at this terminal is the same as at this particular location, right? The same is true here, right? The voltage here is the same as the voltage here, right? So if there's no resistance, then there's no changes to the voltage, right? It's just like you are not changing the elevation of the water. If there is an electric component with non-zero resistance, right, like this kind of thing, like a resistor, or after we talked about impedance, then impedance is more like a generalization of resistance, right? After we talked about impedance, you'll see that it's just like a resistance. So if we have a resistance or impedance, right, the voltage will change across this electric component, right? So if you have something that's has a resistance, then the voltage is going to change across it, and there will be a voltage difference across this particular component. Usually we don't really say voltage difference, right? We don't say voltage difference, we just say voltage across a particular component or something. But what we actually mean is actually the change before and after the change in voltage before and after this particular component, or across that electric component. Right? That's what we actually mean. It's not the voltage of the entire circuit. It's the change of the voltage across a particular component. Right? And this voltage change across an electric component can be measured using a voltmeter. Right? Sometimes the ammeter and voltmeter are sort of combined into the same instrument, but with a different with a dial that allows you to choose if you want to use it as an ammeter or if you want to choose it as a voltmeter. Right? But if you are using it as a voltmeter, you have to connect in parallel with the electric component you are trying to measure. Right? It has to be connected in parallel. The voltmeter usually has a resistance that's kind of a much larger than any normal resistor. So it's going to appear as a wall that's going to almost completely block the flow of current. Right? So as a result, most of the current will still flow through this normal resistor, right? Because this is a wall that's blocking the flow. So most of the flow is going to flow through the normal resistor, and the voltmeter is not going to disturb the entire circuit in any significant way. So that's current and voltage, right? Now let's talk about different kinds of different kinds of electric components that we can actually use to represent, that we can use inside of a circuit, right? There are three major types of the so-called passive components that are used very widely in electric circuits. The resistor with a resistance of R measured in ohm. The capacitor with a capacitance of C measured in farad. And the inductor with the inductance L measured in Henry. The reason that they are all called passive components is because they cannot create power or amplify signals all by themselves. So that's the reason they are called passive. And enjoyings of electric circuits, these three types of components are represented using these three symbols. It's this kind of zigzag for resistors, two parallel lines for capacitor, and this kind of curly thing for the inductor. Right? These are the symbols that are used in enjoyings of electric circuits. And in actual circuits, in reality, these components, which can always be purchased almost everywhere, right? They are very cheap. They are not really that expensive, actually. They may look like those things in the picture. So a resistor may look like this kind of thing, right? But depending upon the ohms, the resistance, its size could be different, and the rings sort of painted on the resistor could be different, right? Those rings, the different color rings actually tells you the number of the amount of resistance for this particular resistor, right? And then capacitor looks like that, right? And then inductor looks like that, and but depending upon the packaging and also depending upon how these kind of components are actually made of, they could look quite different from these pictures. So the resistor is mainly just a energy dissipation device, but the capacitor and the inductor are actually energy storage devices, and later on we're going to see how they actually store energies. The most important thing for us to remember is how the voltage across them, or the voltage change across them, are related to the current that's flowing through them. We have three equations here. So for the resistor, the voltage E as a function of time equals to the voltage across the resistor equals to the current flowing through it multiplying the resistance R. Right, so it's basically telling us that the voltage is proportional to the current with the constant of proportionality given by the resistance R. Right. And then for the capacitor, the situation is quite different. Right, the equation is actually telling us the current flowing through it is actually proportional to the rate of change of the voltage across it, and with the constant of proportionality given by the capacitance C. And for the inductor, it's actually the other way around. If you look at these two equations, right, here it's dE over dt, the voltage over dt, right? But here it's di over dt, the current over dt. So the voltage for the inductor, the voltage across the inductor is proportional to the rate of change of the current flowing through it, with the constant of proportionality given by the so-called inductance L. Right. I've mentioned that the resistor is an energy dissipation device. So the power dissipated by a resistor with the resistance R is given by the voltage across it multiplying the current flowing through it. Right. Considering the voltage across the resistor equals to the current multiplying the resistance R, right? So E equals to this thing in the square bracket, right? And then if we do some algebraic manipulations, we obtain this equation. So the power equals to the current flowing through it squared, multiplying the resistance, right? And considering that the voltage across it also equals to, and another way of representing the power is to recognize that the current equals to the voltage across the resistance dividing the resistance. Right. That's another way of looking at this particular equation, right? So the current actually equals to voltage dividing resistance, right? So in this particular equation for the power, we can actually replace current with voltage dividing R. Right. If we use this particular representation, then we obtain a different formula for the power, which is the voltage squared dividing the resistance R. Right. But both of them are actually equivalent. And depending upon the particular situation or particular measurement that you have, right, if you have a measurement of the voltage across it, you can use this equation to compute the power. Right? But if you have a measurement of the current that's flowing through it, then you can use this equation to compute the power. Right? And that's the power that's being dissipated by the resistance. It's basically lost. It's a losted power. You cannot actually get it back. So it's not like an energy storage device. There's no way for you to actually retrieve the energy. The energy is dissipated. It's just lost. The capacitor is a device that can actually store electric potential energy. Right? As the current actually flows through it, it can accumulate electric charges on its two parallel plates. So we're actually looking at two conductive parallel plates here. Right? The symbol looks like that, right? And the two bars actually represent the two conductive parallel plates. Right. So positive charges will accumulate on the plate where current flows into it. Right. So current actually goes this way from the positive side of the source. It's going to go this way. So current is going to flow into the capacitor in this direction. Right. So positive charges will accumulate on the plate where current flows into it. And then negative charges will accumulate where the current flows out of it. There are attractive forces between those positive charges and then the negative charges, right? That's because if you have a positive charge and a negative charge, they're going to attract each other, right? But because of this kind of dielectric material that's kind of separating the two plates, so the positive and negative charges cannot move toward each other. So during this kind of process, there is a electric potential energy. You're separating positive charges from negative charges. So there's a potential energy that's being built up between these two plates. And the capacitor is sort of known as a potential energy storage device. So our analogy, one analogy that has been used quite often, is to compare the capacitor with a water storage tank with some inflow, right, and some outflow. The outflow is not drawn here, but the inflow is drawn here, right? With some inflow and some outflow, and it has reached a steady state. So the water volume inside the tank is not changing. So it has reached a steady state. So the total amount of water inside the tank is just like the total amount of charges that have been accumulated on the capacitor. Right? The voltage across the capacitor is just like the height of the water column inside the tank. If you think about it, the voltage is just like elevation, right? Which is associated with the gravitational potential energy. Right? The height of the water, the height of the water column in the tank is also associated with the kind of gravitational potential energy of the water column. Right? And then the capacitance C is just like the cross-sectional area of this particular cylindrical water tank. So the total volume of water in the tank, V, actually equals to the cross-sectional area multiplying the height of the water column. And then the total electric charge in the capacitor, Q, right, actually equals to the capacitance, C, multiplying the voltage, E. Right? So if we actually so Q, if the electric charge accumulated across the capacitor equals to voltage times capacity C, right? Once we have this particular equation, what we can do is to take a temporal derivative on both sides of the equation. So on the right-hand side, we have C is a constant; it doesn't change with time, but voltage does change with time. So dE over dt, right? And then on the left-hand side, we have the Q, right, which is the charges, accumulated charges as a function of time, right, taking a derivative of Q with respect to time. Right. The important thing for us to realize is that dQ over dt is actually the current. Right. So at the beginning of this video, when we were talking about current, we're saying that current is the amount of charges flowing through a particular location within a unit amount of time, right? So here it's actually telling you it's actually the rate of change of the charges at a particular location, right? So the current actually equals to dQ over dt. And this equation is exactly the same as the capacitor equation that we have seen on this particular slide. And another way of sort of writing this particular equation is to do a temporal integral, to do a time integral on both sides of the equation, and then rearrange it, right? So if we do a temporal integral over dE over dt, if we multiply dt to this side of the equation, right, and do an integral over dE, then we get E, right? The voltage as a function of time actually equals to 1 over C. The integral of current over a certain time period from t0 to t, right? And then plus the initial condition, that's the voltage at time t0, right? So this integral equation also has a quite a significant meaning actually. So how do we actually understand it, right? So this equation tells us that for capacitor, the voltage across it depends upon the history of the current flowing through it. If there is an initial condition, a non-zero initial condition, right, then the current voltage at time t will depend upon that particular initial condition, right? And this temporal integral also tells us that the current voltage depends upon past voltage, right? So if you write this particular temporal integral as, for example, t0 through t1, and t1 is before t, for example, right? And then this temporal integral actually gives you what? It gives you the voltage at time t1, right? And then you have another integral that goes from t1 to t, right? So the voltage at the current time t actually depends upon the history of the voltage, right? It depends upon the past voltage. So a capacitor is a device that can actually remember past voltages. So it's a device that can have a memory of past voltages. And I was saying that the capacitor and the inductor are both energy storage devices. So how much energy is actually stored in a capacitor, right? The amount of energy stored in a capacitor equals to the temporal integral of the power, right? And the power equals to the voltage times the current. Right? For capacitor, the current equals to the temporal derivative of the voltage multiplying the capacitance C. Right? That's exactly this equation here. Right? We're basically just replacing I with C times dE over dt. Right? And then dt and dt cancels out. Right? C is a constant. You can move it out of the integral, and then it becomes C times E over dE, E multiplied dE. Right? And this integral can be carried out explicitly. It equals to 1/2 E squared. Right? And then if you multiply in C, you get this expression for the energy. Right? So the energy stored in a capacitor is proportional to the square of the voltage across the capacitor. Right? Voltage, we are comparing voltage with elevation, right? Elevation is associated with some kind of potential energy. Right? So voltage is also associated with some kind of potential energy, and this is the electrical potential energy. Right? So it's a potential squared multiplying C multiplying 1/2 that gives you the energy. So it's a form of potential energy. It's a form of electric potential energy that's being stored inside of the capacitor. So now let's talk about the inductor, which is actually a kinetic energy storage device. Capacitor is a potential energy storage device. Inductor is actually a kinetic energy storage device. Back in the 14th video 14, we talked about Ampere's law, right, which tells us that current flowing through a wire can induce a magnetic field. Right? And we talked about solenoid, which is a conductor wired into a coil. And the magnetic field induced by the current flowing through the solenoid is concentrated, so in the center of that solenoid. Right? The inductor is actually a solenoid. It is created by coiling up a conductive wire around a piece of a ferromagnetic material. The black stuff in the middle is a ferromagnetic material. Right? In video 14, we also talked about Faraday's law, which tells us that changes in magnetic flux can induce a voltage. So inside of the inductor, if the magnetic flux changes with time, it will create a induced voltage. And if the current is, if the circuit is closed, then it's going to create a induced current. Right? But how is this magnetic field induced current going to interact with the original current that flows through the coil and creates the magnetic field, right? So that's the kind of question that people have asked in the past, right? So when we were discussing Faraday's law, we did not exactly consider the direction of the induced voltage, right? Here we have an expression for computing the induced voltage, right? It's called electromotive force, EMF. But what's actually the direction of that voltage, right? We talked about directions of voltages, right? You have positive and negative voltages depending upon how you actually measure the relative difference between the voltages at two different locations. So what's actually the direction of the voltage, right? So a voltage does have a direction because it has a sign, right? In the past, we haven't actually paid attention to the voltage, but in fact, there should be a minus sign. There should be a minus sign in front of the expression for the induced voltage, right? There is actually a physical interpretation of this minus sign. It is called the Lenz law. So the direction of current induced in a conductor by a changing magnetic field due to Faraday's law should be such that it will create a magnetic field that opposes the change that produced it. So the Lenz law is actually very similar to the Newton's third law in mechanics. If there is a force, there must be a counter force. So the situation is actually quite similar to how the water wheel actually works. The flowing water mass has kinetic energy in it, and it pushes on the pedals of the water wheel. The pedals of the water wheel also pushes back on the flowing water and exerts a counter force that tries to slow down the water, right? And during this kind of interactive process, this kind of push and a counter force, this kind of interactive process, the kinetic energy stored inside the flowing water is then converted into the kinetic energy of the rotating wheel. And inside the inductor, the induced magnetic field is just like the water wheel. It is storing the kinetic energy of the flowing electric current. Right? The inductance, the concept of the inductance actually characterizes this kind of a behavior of an inductor. Right? And it is defined in terms of the derivative of the induced magnetic field, or induced magnetic flux, or the opposing electromotive force EMF with respect to the current. So if we rearrange this particular equation, then we have d phi equals L times di, right? And once we bring this definition of inductance into Faraday's law, here it's actually Faraday's law, so voltage equals to rate of change of magnetic flux. But here we are using derivatives, right? In the past we have been using this kind of delta. It's a finite change, right? But you can actually convert that into a derivative, right? Without any kind of difference, actually. It's pretty much the same thing, right? So once we bring d phi equals to L times di into this particular equation, then voltage equals to the inductance times di over dt, right? And this particular equation is exactly the inductance equation that we have seen in a previous slide, right? Voltage equals to inductance multiplying the temporal derivative of the current, right? So the energy stored in an inductor is again the integral of power over time. If we bring the inductor equation into this particular integral, right? So power equals to voltage times current, right? And then if we bring the expression for voltage into this integral. Voltage equals to inductance times di over dt, right? And then multiply I, and then multiply integral over t, right? And then cancels out dt and dt cancels out. It becomes integral over I times di. So I over di, I times di. And again, this integral can be carried out explicitly. It equals to I squared divided by 2. Right? And then the energy is proportional to the square of the current, right? Which is actually a electric kinetic energy. So, so the inductor is a kinetic energy storage device.